Thier and Bott, Gilliman and Sternberg, and the first people bringing the two sides together were probably Kirwan and Ness, Linda Ness, student of Kempf, and later wife, and afterwards divorced. Sorry? Oh, she was. Aha. So the other was just a rumor. Okay. Then on the symplectic side, for me, an important inspiration is the work of Donaldson, which comes from various infinite-dimensional analogues of this picture, into which I won't go at all today, and especially his recent joint work with Chen and Sun on the analog in Kaehler-Einstein geometry. And in fact, for me, and in this whole picture, the work of Chen and Sun plays a crucial role in understanding from a differential geometric viewpoint geometric invariant theory. And I would point out at which there are three specific places where their work comes in a crucial manner, which I will explain. So let me start by discussing the setup that I will consider. First object is Kaehler manifold, closed Kaehler manifold x omega j. Usually in the algebraic geometric setting, one also imposes condition that there's a line bundle whose curvature is omega, essentially. This condition, in what I discuss, will not be needed, and the story can be extended. And then the next thing one has is a compact Lie group acting on X, and I want to assume throughout that this Lie group is contained as a Lie subgroup of the unitary group of some vector space. And the hypothesis is that this action is by Hamiltonian symplectomorphisms. So in symplectic geometry, that means if we consider the infinitesimal action of the Lie algebra of G, then we get a map to the vector fields, of course. And let's fix a point X in our manifold, and then we get a map that assigns to every Lie algebra element the vector field at that point. And this map, it's convenient kind of to also give that a name, Lx, as a map from Lie algebra. So the tangent space, and the condition is that this vector field is Hamiltonian. And then one can consider a linear map which assigns to every psi this vector field, and write the Hamiltonian function associated to this. It also depends linearly on psi as the inner product of mu and psi, where mu is a map to the Lie algebra. And so here I'm assuming that the Lie algebra is equipped with an invariant inner product. Otherwise, it's more natural to let the moment map go to the dual of the Lie algebra, but that in our case doesn't make a difference, because in any case, the key ingredient in the whole story is the moment map squared and its gradient flow, its negative gradient flow. So the Hamiltonian condition means that the derivative of this function is the same as the one form that I get by constructing this vector field with omega, and that can be translated into the formula that omega of Lx psi, that's our vector field, with some other vector x hat, is just the derivative of our function, and the inner product with psi. And then another condition that one imposes is that this is a G equivariant under the conjugate action of the group on its Lie algebra, and that translates, on the one hand, one can write it as mu of u x is equal to u mu of x u inverse, or the infinitesimal version of this equation is that the if I plug in for x hat another infinitesimal in another vector field generated by another Lie algebra element eta, then this left-hand side is the Poisson bracket, and the Poisson bracket should correspond to the Lie bracket of these two elements. So I get Lie bracket psi eta mu of x with psi eta. So these are the three conditions that tell us what an equivariant moment map is. And now the next important ingredient in the story is the complexification of this group, and that's kind of nice and easy to write down if we assume that our group is contained in the unitary group. Then GC can just be written by polar decomposition as the set of all matrices of the form x of I eta times u, where u is in the original compact Lie group and eta in the Lie algebra. And then in this situation, we have that on the one hand, G is a maximal compact subgroup of GC, and on the other hand, we have the Lie algebra of this group is also the complexification of the Lie algebra of the original compact group. And we have again an infinitesimal action which we need, which is just obtained by taking a map, an element xi plus I eta, and using j instead of I, right? So that goes to Lx xi in that notation plus j Lx eta. And that whole thing I'm going to call Lxc. So these two conditions, that G is a maximal compact subgroup of GC and the fact that its Lie algebra is a complexification of the Lie algebra of G, also are equivalent to a nice universality property of this group, namely that if you have any group homomorphism from G into a complex Lie group, then it extends uniquely to GC, into the same complex Lie group. And for example, you can take as a complex Lie group the group of holomorphic automorphisms of X, right? And then as a target group, and then you see that GC will act on X holomorphically. And the infinitesimal action is exactly this map, and that's also Lie algebra homomorphism. So that's the basic setting. And now this extended action, of course, no longer preserves the symplectic form. It no longer satisfies any nice equivariance properties with respect to the moment map. And now there are these questions, what subspace to take for X to divide by GC and to get a nice answer. And that kind of is reflected in the three basic definitions. See, in symplectic geometry, there's also a quotient. And it's the Marsden-Weinstein quotient. And that quotient is obtained by taking the preimage of 0 under the moment map that's invariant under the group, and then dividing by the group. And in nice cases, that's a manifold, sometimes an orbifold. In general, it will be highly singular space. And so from that point of view, what one has to take on this side is those elements of X whose complexified group orbit passes through the 0 set of the moment map. And then there are two other conditions. So X in X is called, one is the condition mu semi-stable. If one slightly relaxes this condition and only requires that the closure of the orbit passes through the 0 set of the moment map. So that's GCX intersected mu inverse of 0 is non-empty, the closure of it, and then the condition that the actual orbit goes through is the polystability condition. So if GCX in itself passes through the zero set of the moment map, and the third condition is mu stable, that's the strongest, and it says that polystability is satisfied, so and in addition that the isotropy subgroup, the complex isotropy subgroup of X is discrete. So you could rephrase that as saying that the kernel of that linear rest operator, LXC, vanishes because that kernel is precisely the Lie algebra of the isotropy subgroup.
What's the difference between semi-stable and polystable?
The closure only has to go through mu inverse of 0. The orbit itself doesn't even need to go through it. And semi-stability also does not have any condition on the isotropy subgroup. Yeah, the bar is absolutely important. So, so this then becomes a true formula if one puts a little PS here and only considers the polystable points. And then that will be the singular space. And then if we delete the P, then we also have to here only take those points for which the moment map is regular, i.e. the derivative is surjective, and then there's an honest-to-God isomorphism between two orbifolds. So that's the basic setting, and roughly speaking, from one point of view, one can say geometric invariancy deals with the problem of finding out which points in the manifold are semi-stable, which are polystable, which are stable, and find some criteria for that. And then there's one crucial ingredient in answer to this question, and that's the notion of a weight. So in algebraic geometry, the notion of the weight comes from starting with a line bundle over this manifold, and then using the moment map to lift the group action, for a nice choice of the moment map, to lift the group action to the total space of that line bundle. Right? And then one considers a one-parameter subgroup of or group G or GC, and then consider a limit point, which is then in the manifold X, which is fixed under the one-parameter subgroup, and then look at the action of the one-parameter subgroup on that line bundle, on the fiber of that line bundle. And that is given by an integer. And that integer is the weight of that one-parameter subgroup and the point you have started with, whose orbit you're considering under this one-parameter subgroup. And in the absence of a line bundle, you can still give a meaning to this notion, and that's the crucial second definition. You take a point X and X, and also we don't need to have a one-parameter subgroup. As a matter of fact, we can take any element in the Lie algebra, the uncomplexified Lie algebra that isn't zero, and then you can assign the weight depending on the moment map mu to this pair x psi, and it is simply the limit as t goes to infinity of the inner product of mu of x of I t psi x with the vector psi. So it turns out that if one does has this lift and one has this line bundle, then this is exactly the right notion for the weight. So there's this weight. And now, with these definitions, I'm basically ready to state what I would consider the three main theorems of geometric invariant theory. And they especially important in the Donaldson picture of this whole story. So here's theorem A. That's what we call the moment weight inequality. And the assertion is that if you take the weight, actually with the sign conventions that we're choosing here, you take minus the weight divided by the norm of xi, and then it's always less than the norm of the moment map on the complexified group orbit. And you can phrase that in this form: supremum of minus w of x xi over the norm of xi. Remember, we have an inner product on the Lie algebra. So you take all xi in the Lie algebra non-zero. It's less than or equal to the infimum of the moment map of gx, norm of it, over all elements in gc. And that, for me, that's sort of the heart to understand. It was the key point to understand geometric invariant theory from this differential geometric viewpoint, and I've struggled a long time to understand this inequality. And now I understand 3 proofs of it. So at least one of them I want to describe today. And another thing that's very important is that equality holds in this if whenever, let me say it like this, whenever the right-hand side is strictly positive. The left-hand side sometimes can be negative. And since, in fact, the left-hand side is negative in the stable case, and more generally, you have equality whenever x is not stable. So that's the moment weight inequality. Then the other 2 theorems, theorem B is essentially due to Mumford, and at least part of it. It has 2 statements. It's that let's define the function mu from x to the reals by, so define by the formula exactly the same as that, except that we only consider xi to be generating 1-parameter subgroups. So lambda for me is the set of all xi in the Lie algebra, take away 0, such that x of xi is 1. Right? And similarly, you can define lambda c, set of all zeta in gc, take away 0, such that x of zeta is 1. Okay? So this definition mu is almost the same as that, except that the supremum is taken over all lambda. Right, so I define mu of xi to be the sup over all xi in lambda over minus w of w mu, I should say, because the weight does depend on mu, so always think of a mu there, of x xi divided by the norm of xi. And the theorem has 2 statements. The first is that mu is gc invariant, which for me, actually, I must say, when I started to think about these things, was a key hurdle to understand this, because I guess if I had read Mumford's treatment earlier, then I would have understood it earlier. But so this is highly non-trivial. You can't see it from this formula, that it's GC invariant. And the second is that this definition of mu is equal to that one. So mu of x is equal to the same sup over all xi in g take away 0 of of the same expression. And that both statements are very non-trivial, because the second statement, even though it looks very plausible that if you take the sup over all g or the sup over all lambda, but the function is not continuous in psi. So it's also the second second statement is a non-trivial fact. And then the third statement, and that's sort of classically the main theorem of algebraic geometry, of the algebraic geometric story of GIT, is the Hilbert-Mumford criterion. Numerical criterion, and it has three parts. It's a characterization of semi-stability, polystability, and stability, and it says X is mu semi-stable if and only if all the weights are bigger than or equal to 0. So i.e. W mu of x psi is bigger than or equal to 0 for all psi in lambda. And here the restriction to this space of one parameter subgroups is very important. The second is that X is mu polystable if and only if, first of all, this condition is satisfied. So all W mu of x psi are bigger than or equal to 0. And in addition, that if the weight W mu of x psi happens to be 0, then it must be true that this limit here that shows up in this formula, which I'm going to call x plus, so x plus equal to the limit as t goes to infinity of x of I t psi x must belong to the group orbit complexified of x. So that's the only case in which the weight is allowed to be 0. And that would be the condition for polystability, which is not, strictly speaking, the original form of the Hilbert-Mumford criterion. It's really the first statement that's the original form. And the last statement, which is saying that x is mu stable if and only if all the weights are positive. So that's what I will try to explain. And one thing one can see rather immediately from the formulation here is that if for a moment you believe theorem A and B, right, then you see that if you have a negative weight here, that's the only weights for which the inequality is interesting, and then you get a positive number here, so the group orbit cannot dip down to mu inverse of 0, so therefore it is definitely not semi-stable, right, if you have a negative weight. And the other way around follows from combining these two theorems, because if the if it's not semi-stable, then the right-hand side is positive, so therefore the equality statement applies, and this is equal to that. And if you then also believe that these two supremums are equal, you also have an element of lambda that is negative, right? So clearly, the first theorems A and B imply part 1 of theorem C. Right. So that's one reason why I think this is a very nice way of approaching the subject. And another is that there are very often situations where you have a group orbit which doesn't have, where the infimum is not achieved, and then still you have by considering all these weights, a definite lower bound for this group orbit, and which is in fact even sharp. Right? And let me in fact just mention another corollary, which I also think of as a rather non-trivial inequality, is the Kerr-von-Ness inequality. So if you have an element mu, an element x, which is a critical point of the moment map squared, then it follows from it that it minimizes the value, the norm of the moment map on the complexified group orbit. So it's less than mu of gx for all g and gc. And that's another easy consequence of this theorem A. Namely, all you need to do is here observe that this condition here, by differentiating, means that Lx in this notation, mu of x is 0. And then when you look at the definition of the weight and stare at it for a few minutes, you see that if you put psi equal to minus mu of x, then it is in the isotropy Lie algebra of x, so therefore this point doesn't move, so x plus is equal to x, and you get mu of x here and minus mu of x there, so you get minus mu of x squared. That gives you this lower bound, because the norm of psi is also mu of x, and so you get exactly this inequality of Kirwan-Ness, right? So in that case, the norm of the moment map itself at this point, x, gives you your lower bound, but this inequality gives you also sharp lower bound if you don't have a critical point in the same complexified group orbit. Right? So this is what I would consider the main results of the subject, at least sort of from this point of view. And I want to discuss a little bit the proofs of this. But I probably don't have time to get very far with that, but I will at least make a start of explaining some of the arguments involved. So let's begin with a very simple argument. That
the original proofs are all algebraic geometry proofs?
well, yeah, and see the situation that I should say that the first mention I saw of this inequality was in the paper by Linda Ness with this appendix by Mumford. And there she considered the situation where you have the complexified group, and my notation, the notation that they use is different. They call the reductive group G, and the compact subgroup they call K. And I use instead G and GC. All right, so you have GC acting on a complex vector space V, or Hermitian vector space V, or on Cn if you like. And then GC also acts on Cpn, or on the projective space of V. And in that setting, you have a kind of standard moment map, which is mu of, well, depending on some scaling factor. So the moment map on this side here, right, the moment map of V is the inner product. The scaling factor I call h bar. We call h bar V with I psi V, and divided by the norm of V squared. And if you take that moment map, and then the corresponding weights are related to the eigenvalue decomposition of I psi. So you decompose V into all the eigenspaces of I psi. They have real eigenvectors. Right? One of the confusing points about this whole subject is that psi has imaginary eigenvectors, and I eta has real eigenvectors, eigenvalues. And so in that case, in the eigenspace decomposition, you look at the maximal eigenvector that occurs, and that's the weight. So W mu in a nutshell of x and psi is, in this notation explained in words, the maximum. There's also this factor h bar showing up here, lambda j, where the Vj is non-zero and the lambda j are the eigenvalues of I psi, right? So in particular, you see that if the eigenvalues are negative, so if the weight is negative, then all the eigenvalues that show up in the decomposition for V are negative, and then e to the I t psi goes to 0. And that's the classical Hilbert-Mumford criterion. It's a corollary of the first statement of theorem C. And in that setting is where, with these explicit interpretations of the weights, is where Linda Ness formulated this Mumford, this moment weight inequality. and proved it.
So this generality then is new?
I guess so. I guess it's new in the case where omega, where you don't have the rationality assumptions. Well, partly, one can't really say that. It's not really that new, because if you look at the proof, it's actually, and that I want to come to. So the main point in the proof is an argument of Chen, of Xiuxiong Chen. Sorry?
What's the rationality assumption?
For omega, the rationality is that omega is rational. I mean that up to the usual scaling factor, which is 2 pi h bar, omega is an integral form, right? I mean, lifts to an integral form. And then there's also another rationality condition on the moment map mu, and that is that it's a kind of nice. How shall I put it?
But you don't need these assumptions.
No, you're right. We don't need it, but this is a sense in which what we're doing is more general than it's usually done, right? So, but it's kind of for the symplectic geometers among us. I still mention that assumption.
So μ-GIT means you close it down.
Sorry?
So μ-GIT means you allow irrational. I guess in your title, I guess I can put it.
Oh, no, the mu means the moment map. It's a dichotomy between the algebraic geometric picture and the symplectic picture. And on the symplectic side, we don't impose rationality conditions, right? And so let me write down an action functional assigned to a point x0 and x, a loop in the group, in the original compact group. So U is a map from R mod Z to the Lie group G, and then we get a loop in the space X by doing x of t equal to U of t inverse x0. That's a loop in X, and then we fill it in by a disk. You take X bar, an extension to a unit disk to X, so that X bar of e to the 2 pi I t is x of t, right? And then you can write down the usual symplectic action using the Hamiltonians coming from the moment map, for which this is a solution, and then you get a mu of this triple x0 u x bar is by definition minus integral x bar star omega over the disk, and there comes a plus sign because of all this u inverse from 0 to 1 mu of x of t inner product u inverse u dot of t dt, right? So this action integral has to have the same periods as omega, so it has to be in 2 pi h bar z for all triples, always. That's the condition on the moment map that corresponds to using the moment map for constructing a lift of the action to the total space of a line bundle. It's this action function, and it turns out that if you stare at it so sufficiently long enough and take your symplectic playbook out of your pocket, then you see that this is invariant in a homotopy. And also, if let's say the group is simply connected, then you can always find a moment map satisfying this condition. And if omega is already rational, right? So that's so these are the rationality conditions which we do not impose. Okay? So let me say a few words about the proof of theorem A. So let me. So here, so proof of theorem A. First of all, for starters, let me prove a simple inequality that doesn't have a g in it, right? And then it's a very easy argument. So, so the easy part, but still it's kind of enlightening to look at this, and it's you consider call this point x0 to not get confused. And consider the curve x of t equal to exp of I t xi x0. The same curve that it shows up in the definition of the weight, right? And then you differentiate this, and then you see x dot is equal to j times, because of the I, times v xi of x, which I write in the form lx xi, okay? So now let's differentiate the following, the function, the inner product of mu of x with xi. So what we find is it's the derivative of mu of x in the direction of x dot, inner product xi, right? Now let's remember that that is the Hamiltonian function for the vector field Lx xi. So this is omega of the vector field Lx xi with x dot. Now that x dot is j Lx xi, so that's omega of Lx xi, j Lx xi, and that since we have a Kaehler manifold, this is precisely the Riemannian metric, so we get Lx xi squared, norm squared, bigger than or equal to 0. Okay? So now that means that the limit of this function is bigger than the value at t equal to 0. So this implies that mu of x0 xi, because that's by putting in t equal to 0, is less than or equal than the limit, which is equal to the weight of x0 and xi. Right? So now put it the other way around and use Cauchy-Schwarz, and you see that implies that minus w mu of x0 xi is less than or equal than minus mu of x0 xi less than or equal than the norm of mu of x0 times the norm of xi, and there's your moment rate inequality when g is the identity, right? So now the question is, what if g is not the identity, right? So if you want it for any g, and now if you for a moment believed theorem B, the part of Mumford, right, that it's a G invariant function, GC invariant function, then you could just take the supremum over all these W's, right, and you get M mu, and M mu of GX0 is M mu of X0, and you get the lower bound that you want, right? That, however, requires to prove that part of theorem B that we need for this argument, right? And instead of that, I want to explain an argument of Chen that gives this proof. For that argument, one would need actually, I haven't checked if it also carries over to all xi and g, but up to now, for that part of the story, I would need that xi is in lambda, right, to make that work. So instead, the argument of Chen, that is based on a certain geometric picture that's already implicit in this little calculation. And that geometric picture is there is a function on the space GC mod G. So which we call the Kempfness Mabuchi function. But purely in the finite dimensional setting. And so this function I want to call phi x0, which goes from GC mod G. Well, let me put it like this. First I have a function from GC to R, right? And then this function we call phi x0. And then it turns out this function descends to the quotient by acting with G on the right. So think of GC as a principal bundle, as a principal G bundle, and go to the quotient. And then you have GC mod G, this space here. And then this function descends to that quotient. And the condition of this function, roughly speaking, just a condition on the derivative, namely that d phi x0 of g in the direction of g hat, which is a tangent vector of gc at the point g, should be equal to minus the moment map evaluated at g inverse x0 times the inner product with the imaginary part of G inverse G hat, right? So notice that if you have a tangent vector of the Lie group at a point G, you can transport it back to the identity by G inverse. In this case, multiply on the left. It seems it's a natural thing to do here, and then you get an element in the complexified Lie algebra, and you take its imaginary part and take the inner product with the value of the moment map at this specific point. And that gives you one form. Then you check that this one form is closed. So then you observe next that this one form descends to this quotient, and for that you need that if G hat that it's trivial on the vertical space, that's sort of almost you can see, and then you also see that it's equivariant under the G action, because if you put a G on the right, a U on the right of G, then it goes on the left, becomes U inverse U, and here it also goes on both sides out, and then you use equivariance of the moment map and invariance of the inner product to show that it descends, right? So then you have this beautiful function, and now it turns out that this function actually is exactly what's going on here, right? So what's going on here is that this mu of xi is already the derivative of phi along this curve, and therefore d by dt of this is the second derivative of phi along the same curve. Now this curve, turns out, is a geodesic in this quotient space. So here the geodesics have the form, more precisely because we act on the right, also the geodesics have the form G0 exp of I t eta. These are the geodesics, equivalence classes of these guys. And so this here is a geodesic, and so phi x0 is convex along geodesics because of the same calculation. Right? So that's in other words, is a rephrasing of this calculation that it's convex along geodesics. Right? So now one has this Kempf-Ness-Mabuchi function, and that's also in a very beautiful way related to these three concepts that were somewhere on some blackboard, but not anymore. So this convex function, and one can check that very easily. In already, it's interesting to look at circle actions on S2, and then think of this as a height function, the moment map, and then shift the two spheres so that sometimes 0 is a critical level, sometimes the image doesn't contain even 0, and sometimes 0 is a regular value in the image. And then you see that that changes the behavior of this Kempf-Ness function, Kempf-Ness-Mabuchi function, that in the stable case, it's bounded below and proper, and in the unstable case, where it's not even semi-stable, it's not bounded below, and the semi-stable case is bounded below, and in the polystable case, it's bounded below and has a critical point. And that polystable case is kind of obvious because the derivative is a moment map. Right. So there's some interesting correlation, which one can think of the generalized Kempf-Ness theorem in this setting, the characterization of, in the absence of a line bundle, you can characterize these various stability notions in terms of the behavior of the function phi. And that's sort of the analog of Kempf-Ness. So now let me go on to prove, to explain Chen's proof of theorem A. And the best thing to do this is as maybe first a picture. Let me give you a formula and a picture. So I guess we don't need this theorem anymore. So this is Chen's proof of theorem A. And which he wrote down in an infinite dimensional setting of actually the Mabuchi functional and Kaehler-Einstein geometry, and which carries over very beautifully to the finite dimensional setting, as he explained to me in August in Dalian at a conference, which was kind of a breakthrough for me to understand the whole picture here, which I had been struggling with for a long time. Okay, so let's take a point x and x, but now we also have the element g and gc, and then we have xi and g take away 0, so also no lambda condition here. And then the formula says there exists an eta of t in the Lie algebra, and there exists, that's just by definition of the complexified group essentially, exists the u of t in g, so that, let me write the formula like this, exp of minus I t xi, exp of I eta of t, u of t, is equal to g inverse. So now let me draw you a picture to this formula. So here is a geodesic in GC mod G. And this geodesic is given by this expression. So it's gamma of t equal to the equivalence class of exp of minus I t xi. Right? So it goes through the origin being the matrix 1. Right? There's a geodesic starting from there at t equal to 0. And now somewhere here is our point G inverse, or the equivalence class thereof. And what does this mean here? If you put an S here, then this is exactly the geodesic running from, for S equal to 0, it's this point, to G inverse, right? So I take some point on this geodesic here, and I take another geodesic running into the direction of G inverse. So now this, the tangent vector of this geodesic is eta of t. And the tangent vector of this geodesic in the reverse direction is actually, if you go interval time 1, it's t times xi. And that's because of the minus sign. I don't need a minus sign here, right? So now, now we have negative curvature. This I didn't say before, or did I? So GC mod G is a negative curvature manifold. This means that the difference between these two vectors is less than the distance between these 2 points, right? So you have the inequality that t xi minus eta of t is less than a constant c, which it is I don't care about. And that implies, by normalizing the vectors, so this t goes to infinity, right? So it implies that the limit of eta of t divided by the norm of eta of t is exactly xi divided by the norm of xi. Now, there's a little estimate that involves, roughly speaking, the same argument that's on this blackboard here. And that's the following. So I have now a sequence of inequalities that I need to write down. And that has to do, the geometric picture is the following. You look at this function phi x along this geodesic, and we know it's convex along this geodesic, and you compare the slopes at this point where they meet. The slope of this geodesic and the slope of that geodesic. And then the error is going to be very small. And that's going to prove the moment weight inequality. But let me write it down. So you start with minus mu of gx, and then you use Cauchy-Schwarz and say that's less than mu of gx in a product. Now you have to choose the right vector. If I can read my own writing, u inverse eta u, and divide by the norm of eta. Now that's a true inequality by Cauchy-Schwarz, okay? And then what we do is we now use this definition, and no, we use that inequality. So if we walk from this point gx a little bit in the direction of that geodesic, in fact for time 1 along that geodesic given by u inverse eta u, then we get something bigger, right? Because this inner product is increasing. So that's the crucial inequality is less than mu of, now you take exp of I u inverse eta u gx close bracket u inverse eta u divided by the norm of eta. So now we investigate this expression that I've just written down, right? And using that formula over there, and then you see what you get is equal to, on the right-hand side, so what is it equal to? Mu of, right? And so let's pull out the u inverse on the right-hand side and the u here. You see x by eta ug. No, there's the inverse here, right? So you put the g on the other side, x by eta ug is just x of minus it xi. So you get u x of minus it xi. It's very easy to make a mistake with all this bloody conjugation. And then you have u inverse eta u divided by the norm of eta. Now you see what's happening. The u goes out, becomes conjugation, cancels this u on the right-hand side. So you get mu of exp of it xi x, right? And take eta only. The u disappears completely from the picture. And now you see eta divided by norm eta. You let t go to infinity. This goes to xi. And the whole thing goes to the weight, right? So this converges, st goes to infinity, to w of x xi divided by the norm of xi, right? And that's the moment rate inequality, right? By putting the xi on the other side and so on. And so this, I think, is a very beautiful argument for the moment rate inequality in general. No, that doesn't completely prove theorem A. Sorry?
It does in infinite dimensions. There's some compactness that's built in there.
No, the crucial thing that goes into his proof is this beautiful theorem of Chen, actually, that there exists this geodesic. So his big existence theorem for geodesics in the space of Kaehler potentials, which is the Monge-Ampere equation, and he proved the existence of a C11 geodesic. So what that means is that this space is not only formally a negative curvature manifold, but actually a negative curvature metric space.
Quite trivial. In this limit here, you seem to be using the fact that the normalized length.
Yeah, but that argument carries over to his case. You take the point xi is given, and you take the geodesic connecting them, whose existence he proved, and then this negative curvature estimate that the angle shrinks is just exactly the same as in finite dimensions. Yeah. So that's the story of theorem A, and I think I'm out of time. Let me just mention two more things. One is that also there's a crucial argument of Chen and Sun going into the picture, into the proof that the inequality is sharp when in the unstable case. And what they do there is, so they consider gradient flow line, and then there's this correspondence between gradient flow lines of the Mabuchi functional, the Kempf-Ness Mabuchi functional, and the gradient flow lines of the moment map squared, and then you connect 2 points by a geodesic, and then you let the limit t go to infinity, and that's how they find the optimal, what we call the dominant mu weight in this picture. There's one argument in the third place where their arguments come in is in the proof of theorem C for polystability, the sufficiency of the condition, because there is the intermediate step that the first condition implies a classical Hilbert-Mumford criterion, and that you can use to prove the second statement of theorem C. And then the third statement is an easy consequence. So don't have time to go into details, but thank you very much for listening.
Thank you very much.